Today we're going to talk about the basics of electricity. Now, most of this, the majority of this will be things you've done before at GCSE, so this should be a fairly kind of straightforward bit of recap for you. Hopefully you think about things again from a fresh perspective. And what we're going to do is we're going to start off thinking about the structure of the atom. So what I'm going to do is I'm going to very quickly just draw an atom for you. Now, if you do chemistry as well, I apologise for what I'm about to do. This is going to be, I'm going to butcher a bit of chemistry here. But from physics, we need to have a basic understanding of atomic structure, as you know. So let's say I've got an atom, and this is a generic atom, and if I get the number of electrons wrong, then I don't care. So please don't shoot me. I'm not interested in what's going on here. All I'm interested in is this outer shell, which we call a valence shell. Now, if I've got one single electron in that outer shell, and this happens in things like copper, gold, lots of sort of highly conducting metals, I get this outer shell, okay, with one electron. Okay, so we call this a valence electron, and essentially it can leave and rejoin this atom, and it's really, really important. In fact, it's absolutely crucial to electricity and to our understanding of how electricity works that we understand that we have an electron which can essentially be free and move. So let's imagine I've got a sort of cross section of piece of copper wire or gold wire or something like that, and inside I've got all these atoms. Okay, I've got all the atoms. Let's say it's copper. These are all copper atoms, and if these are the nuclei, then these free electrons essentially can travel around totally randomly within this wire or within this metal. Okay, so I've got all these electrons flying around in random directions, just doing whatever the hell they want and having a good time. Now, let's talk about electrons briefly. So, an electron, okay, a negatively charged particle. Okay, it has a relative atomic charge of -1. We call it -1, although this is fairly arbitrary. Remember, with a proton we have +1. I'll talk about that as well. And these are single units, but the actual charge on an electron is -1.6 times 10 to the 19 coulombs. Okay, so that is the charge of one electron. So it should make sense that the charge of a proton is plus 1.6 times 10 to the 19 to be the exact opposite. Okay, but overall, all these little electrons have an individual -1 charge. Okay. Now, let's draw another diagram. Let's say that what I do is I have my wire, my copper wire, with all these free electrons flying around. Okay, and let's say that what I actually do is I get a battery, or what's known as a cell. Okay, and we've all seen a battery. Let's pretend it's a AA battery. There we go, that's the positive end. And we have the other end, which is a negative. And let's draw on these nuclei again. Now, if I stick a battery at one end of this wire, all of these free electrons, which are negatively charged, are all going to want to go in one direction. Okay, they're all going to travel towards this positive terminal. Okay, and that's because obviously, as we know, if I have a negative charge, it's going to be attracted to a positive. Okay, so I get this flow of electrons moving towards this positive end. Okay, and that's what we call electron flow. So these free electrons are going to be attracted towards this positive end of this battery, okay, or this cell. And if I was to put the Y on the other side, they'd all move the other way. Now what's really important is the electron flow here is negative to positive, but I'm going to draw an arrow here because this represents something we call Can I spell? That's a real question. Can I spell? Convention. Convention. Yes, I can. Conventional flow is the other way. Now, conventional flow, convention comes from, as in what people have always done. So conventional flow basically is the wrong way, if you think about it. Electron flow is this way, conventional flow goes the other way. That's something you need to be really careful about, because if I draw a circuit, in fact I'm going to draw a short circuit here, why not? Then conventional flow, the electron flow is going to be negative to positive, so the electron flow is going to be this way. Okay, that's the way our electrons are going. But my conventional flow obviously is positive to negative. Okay, so that's my convention. So you need to be really careful about that when we look at circuits. Okie dokes. So if you're happy with the idea that free electrons flow within a metal or within a conducting sort of medium, and they flow towards a positive, then we can get the basics of currents and charge going. So, okie dokes. Let's pretend we've got a certain point. So I'm just going to draw a sort of a really rudimentary sort of donut here. Okay, and here I have a wire passing through it. Now, if I have all these electrons, and all these electrons are passing through this point, okay, and you can imagine the ring I've just drawn is like an ammeter, okay? So all these electrons are flowing through, having a great time. Now, the charge transferred at this point is literally, which I call change in Q, is the number of electrons that have passed through. Okay, so the number of electrons that pass through, all we do is we take our electron charge, which we know is 1.6 times 10 to the 19, and we just times that by the number that have passed through. So that gives me my Q. Now that's not particularly useful, how much charge has actually flowed, so we're more interested in the rate of that. Okay, so the rate of charge passing through a point we call the current. Okay, so the current is defined as I, and you know this already, the change in charge over the change in time. And essentially what this means is, well, how many electrons are flowing through per second. Okay, now I'll just go down from here. As we know, I, or current, is in amps, or amperes, and the definition of an amp, 1 amp, 1A, equals 1 coulomb of charge flowing in 1 second. Okay, so it's 1 coulomb per second. Now what is 1 coulomb? Well, a coulomb is 6.25 times 10 to the 18. So that is a lot. That's a very, very, very large number of electrons. Okay, so it's 6.25 times 10 to the 18 times by 1.6 times 10 to the 19. That 1 coulomb, okay, is defined by the electron charge times how many electrons get to that point. Okay, so our first equation we should be happy with. Current change in charge over time. Now you might remember this one as Q equals IT, okay, or you may remember it as the quit one, which is not particularly useful because it's not that hard. It shouldn't make you want to quit. There's far more difficult equations which we've already come across, which would make you want to quit. Okay, let's keep moving. Now, voltage. Voltage is a bit of a sort of strange one because we can define it in a few different ways. Now, voltage really, if we go back to our original battery, the voltage here, okay, is the pull here. It's the pull or push given to these free electrons. Okay, so a battery has a voltage which might be something like 9 volts, and that dictates how much push or pull there is on all these free electrons. So voltage, we can define it in a few different ways. I'll just put here the push of charge. Okay, it pushes those electrons around the circuit. So the first thing we can think about is that the voltage is the push, so it's basically the energy given to each electron. Okay, and we divide this by basically how many electrons there are. So a way of thinking about this is, you know, if you think about energy in terms of you pushing something, well, let's say you push one person, well, that's the amount of energy divided by one person. Let's say you've got the same amount of energy and you're pushing 2 people, well, the push is going to be less, isn't it, overall per person, because you're pushing more than one person. So the voltage, the energy provided divided by how much or how many electrons you're pushing. Okay, so this is the kind of standard way of remembering it, and you might remember this as E equals QV, energy divided by charge. Now, there's another thing called electromotive force, which is, to all intents and purposes, pretty much the same thing, but we call this E with a weird kind of, it's like an epsilon. Okay, so this we define very, very similarly. It's the electromotive force, and this is when we're putting energy into a circuit. So think about this one as a generic voltage equation. The electromotive force is actually, well, that's the actual push, okay, in a circuit. We define it in the same way though. It's E over Q. Okay, and the final way of defining voltage is probably the correct way. So for a component, so if you're actually considering an individual component, we use something called potential difference. Now this is the best way of describing voltage, okay, because if you think about it, it's the sort of push either side of a component. Okay, so if I have a component in a circuit, whatever it is, okay, it could be a bulb. Remember, we put a voltmeter either side of that component because we want to know the difference either side. Okay, so the difference between here and here we call the potential difference. Okay, so the difference between either side of a component. So for this one, it's actually the same equation, but it's written slightly differently. So PD, potential difference, equals W, don't get freaked out, that stands for work done, which remember is energy, so it's the same as up here, and again over charge. But this is sort of, let's get rid of that, shall we? It's slightly different and it's more dictated for a component. Okay, the last thing to talk about before I set you on your way is resistance. Again, you know about this already. Resistance is just the opposition to current. Okay, so it's whatever is restricting the flow of electrons. I always like to think of this diagram. I think this is a useful diagram to look at. Imagine I've got a pipe, okay, and I've got a sort of squeeze in it, a little kink in it. Then the resistance, okay, is this narrowing of the pipe. The resistance is that squeeze there. Now if I have, there's a big arrow, okay, so here's my voltage, okay, here's my potential difference, here's my voltage coming in, big arrow coming in this way, and what actually comes out is my current like this, okay, not as big. Big push, big constriction, and a small current comes out, and that's because it just cannot get through. Now if you think about this at a kind of atomic level, let's say I've got a nice sort of wire like this, and a wire or any component has a certain amount of resistance. The resistance is basically the opposition to these electrons getting through. So for example, if I have a really thin wire, okay, like you might find in a filament bulb, okay, the reason a filament bulb has a really thin wire is so that it gets really hot and then glows red hot. That's where light comes from. Isn't that interesting? So say I've got a really narrow wire, and you can imagine it's much more difficult for these electrons to kind of squeeze their way through. So if you have a narrow cross-section wire, really difficult, okay, so more resistance. Think about that when you think about resistance. You know, that's probably the most important idea for it. So if you have a really narrow wire, or you have a really long wire, it's more difficult for electrons to pass through. Okie dokes. The last thing I'm going to talk about with this is that resistance creates heat. Okay, if we have heat, then these particles, okay, these atoms are going to move and vibrate more and more frequently. Right? If they're clattering around and vibrating, it's going to make it even more difficult to go through here. Now, none of you remember gladiators, but they used to have a thing called the gauntlet, where you had some gladiators in this kind of narrow channel, and you had to try and run through. Now, if they just stood still, easy to get past them, but they were moving around and they were sort of throwing stuff at you and battering you, really difficult to get through. Okay. Now, the other thing is resistance creates heat, but heat also creates resistance. That's not a groundbreaking thing to say. If resistance creates heat, then heat creates resistance. If I've got heat coming from the outside of a wire, then that's going to make it more resistant as well. Okay, so heat is all to do with the vibration, the kinetic energy in those atoms. Okay. Now, the last thing we'll look at today, very briefly, Ohm's law, which most of you will know as V equals IR, as in the resistance is the voltage divided by the current on a component. Now, Ohm's law is a bit of a weird one because it doesn't always hold, but for what we call an ohmic resistor, or an ohmic conductor I should say, sorry, I get a pattern when I plot voltage against current. I get a nice straight line. Okay, this is called an ohmic conductor. Now, this isn't really very true of real life because heat stops this happening, but an ideal ohmic conductor, okay, has a direct proportion between the voltage and the current. Now, you'll know a few more of these graphs. For example, you'll know that a filament bulb has a graph which looks a bit like this. And you'll also hopefully remember that a diode has a graph which looks a bit like this. Okay, so VI characteristics are another thing to remember. Now, the basis of today's lesson is you're going to use everything I've looked at here, all this recap, and you're going to answer some questions. I'm also going to give you some videos to watch, which will be in the chat. Okay, so you'll have 3 sheets to work on, work through them. There should all be a bit of revision though. Best of luck. I'll be in the lesson. Ask me for help. All right, bye-bye now.